All right, we are in chapter 13, and it is on what we call modular arithmetic. Now, some people may have heard of this before, and it's totally fine if you haven't. Most people think about and learn arithmetic by way of a number line. That number line is not very solid. Let's get something solid. Number line that keeps going forever. And we have 0, 1, 2, all our numbers are there, right? 5, 6, and there are even negative numbers. -2 to indicate maybe when you're owing an amount and things like that. And it keeps going forever. And in this conventional number system, I don't want to call it a number system in the same way as the Roman system and Babylonian system, things like that. In this mathematical system, in this, let's call it a mathematical system. Mathematical counting system. We learn 1 plus 1 is 2. 3 plus 7 is 10. 2 plus -3 is -1, and so on and so on. But these calculations, these mathematical statements, are only true in this system. In another system, 1 plus 1 might not be equal to 2. You're working in a specific system. You're counting along this infinite straight number line. But when you look around you, you could see, for example, the standard clock. Now, yes, up here there is a 12 originally. But if you think about the hours counting around, once it hits 12, it keeps going back over and over and over. It's not the same system as this. The hours don't keep going forever. They loop back on themselves and keep going around in the circle. And if you have, for example, 2 o'clock and you add 3 hours, yes, you'll get 5 o'clock. But if you have 10 o'clock and you're adding 4 hours, then it's 2 o'clock. The counting is essentially the same, except we're going around in a circle instead of a straight number line. That's the only difference. And because of that, the answer to any calculation, to any arithmetic question, is going to be one of these numbers. Now, we change the 12 to a 0 because we want the subtraction to make sense as well. That if we say it's 2 o'clock, go 2 hours back, I want 2 minus 2 to still equal 0. So 0 and 12 are equivalent. And just for convenience, to sort of fit with the 0 here, we write 0 instead of 12. So we have this circular counting system. And we'll call this arithmetic. Why is my pen so thick? Modulo 12, or just mod 12. for short. So when I say I'm counting mod 12, it means I'm counting in a circle. And the circle has 12 numbers on it. 1, 2, 12, but 0, or 0 to 11. There are 12 numbers on this circle. And you have to visualize this circle when you're saying even 2 plus 3. Yes, the answer happens to be the same as a number line, but it might not always be. Like 10 plus 4 is now in this mathematical counting system equal to 2. Now, for mathematically technical reasons, we write 3 lines for our equal, but I don't really want to get into that now. If you want to just write an equal, that's totally fine. And we also say it's equivalent to the number. Because in reality, if you want to lay your number line on this circle, 11, and then the next one's going to be 12 and 13 and 14 and so on. You're going to come around again, and that's going to be a 24. So really, the 0, 12, and 24 numbers that I see here, that I'm so used to and familiar with, are all in the same, they're all equivalent. We say they're all in the same equivalency class, and that class is represented by 0. So 24, 12, they're all squishing down to one of these numbers, and 0 in this case. 13, 25, and so on will all squish down and be represented by the number 1. And that's really, we still have all these quantities, but we're counting in a loop. Therefore, the answer will always be represented by one of these numbers. But if you want to just write an equal, you really don't have to worry about equivalency classes or anything like that. That is a little bit more technical. So the essence in this counting system, it's a different system. We are counting on a circle, and your way of doing this, like if you're saying 1 plus 2, you have your little guy there. He's looking to the right. He's taking 2 steps, and he ends up at 3. Everything is exactly the same, except he's not walking in a straight line. He's walking in a circle. Excuse me. So if I stand over here, there's my guy, sideways, because he's walking on a circle. He's looking to add 2, so he takes a step 1 to 2 to 3, and there he is. If he's standing at 10 and he's looking to add, he's going to walk in the forward direction a number of steps and end wherever he's going to end. So everything is exactly the same. The only difference is that I'm counting on a circle. And we call that modulo 12 arithmetic. So I could have technically many different size circles. This one may be a little silly, so let's not worry about that. Let's just get rid of it. Let's paint it away. Let's get rid of it. It's gone. Don't worry about it. It's a little strange when it's barely a circle. Let's look. We can have a size 9 circle. And then it's going from 0 all the way to 8. And 9 would be equivalent to 0. Or I can have a 15 circle. Really any size circle you want. And what we call here the modulus. Let's make a pen that's a little thinner. Maybe a black. That guy is a little better. The modulus, oops, back here, list, that I'm indicating tells me what size circle I'm counting on. So there's no confusion what my counting system is, because I always say, if I'm not counting on a number line, I'm always going to say mod something. indicating the size of the circle I'm counting on is this size, for example, 9. So I could say things like any arithmetic, and we're going to mainly stick with addition, subtraction, multiplication for now, and in the following section we'll see how subtraction a little bit, but mainly division is a little different. Eventually we'll see that. If we say something basic like 1 plus 4, that is obviously 5. Even though I would get the same answer regardless, I do emphasize this circle because sometimes the answer might be different. If I say something like 7 plus 3, that is obviously, I stand at 7, 1, 2, 3 steps, so it's 1, and I indicate my size, circle. Let's say, I'm going to leave a little space here. Let's say, it doesn't really matter, 6 plus 7. Yes, you can stand at 6, take 7 steps, 1, 2, 3, 4, 5, 6, 7, and end at 4. But the walking around a circle, walking around a number line with your little guy looking around is pretty basic. So we want to understand a little better how we get to the answers here. Well, in my normal number line counting system, 7 plus 3 will be 10. It's as if I start at 0 and walk 10 steps around. Because I made a full loop of 9, I really only have 1 left. So if I divide this by 9, the remainder is 1. Because by dividing by 9, I am seeing how many full loops of 9 steps, a full circle, can fit into these number of steps. 1 full loop, how many are left? 1. So I'm going to be left at 1. Here, the total number of steps from start to finish is 13. If I divide that by 9 and ask how many full loops will fit into that, I don't really care how many. I want to know how many are left. Well, clearly 4. 4 is my answer. 1 is my answer. So the answer to a modular arithmetic question is the remainder after I've divided by the modulus. I can extend that. I'm trying to stick on the same page here. Let's go up here by using multiplication to get larger numbers. Let's say I take 3 times 8. I know that is a total quantity of, I wanted to do 4 times 8, sorry. 4 times 8 is a total quantity of 32. If I divide, well, I don't want to actually write the dividing. If I divide that by 9, how many are left? Well, 32 will make 3 full loops of 9, and that uses 27. So 5 are left, and therefore I will end up at the 5 if I've taken 32 steps around. Therefore, 4 times 8 is 5 mod 9. And I can do this in between 32 to help me find the answer. Let's squeeze in one more here. Let's do, I don't know, 5 times 4. That'll give me a quantity of 20 in our normal counting system. There's no 20 here. If I've taken 20 steps from the start at 0, where would I end up? Well, 2 full loops would be 18, 2 left. So that's 2 mod 9. Let's go something bigger. We can change it to a mod 15 circle. Why not? And we can now ask things like, or we can do a -2 eventually. But I'm much more interested now in the plus and the multiplication to just get us used to this. I can say 13 plus 7. I know that's 20. There is no 20 here. Once I've done a full loop of 15, 5 will be left. Ooh, I'm not going to write inside my circle. So the answer is 5 mod 15. It will be the same if you start at 15, if you start at 13 and you take 7 steps, 1, 2, 3, 4, 5, 6, 7, you end up at 5. But you don't have to actually manually do that every time. Let's go 9 times 10 is 90. How many full loops of 15 can fit into 90? How many are? I don't really care what that answer is. I want to know, is anything left over? Well, no, it'll be 15. It's a full loop. Let's emphasize that. 15, 30, 45, 60, 75, 90. So they're all full loops. Nothing is left over. Therefore, I'm back at 0 mod 15. So it's the remainder when I divide by the modulus. It's the remainder after I've divided this quantity by the modulus. That would give me my answer on my modulo whatever circle. Now let's go to our examples. Where is my example? There it is. 13.1. Complete the mod 4 addition and multiplication table, meeting all the possible calculations on the mod 4 circle. And then we'll see if there are any patterns, whatever we can see. So, exercise 13.1. Well, if I'm working mod 4, these are my numbers that I work with. 0, 1, 2, 3. There are 4 numbers. The number 4 is equivalent to 0, and that's why we don't have it. So there are my tables, one at a time. Addition. Now, think about this if you ever need to. So 0 plus 0 is 0, 0 plus 1, and they stay the same. 1 plus 0 is going to be the same. 2 plus 0, 3 plus 0. 1 plus 1 is 2. 1 plus 2 is 3. And those numbers are there as answers. These are the only answers I can have. But 1 plus 3 is 4, which is 0. 2 plus 1 is 3. 2 plus 2 is 4, which is 0. 2 plus 3 is 5, which is 1. 3 plus 1 is 4, which is 0. 3 plus 2 is 5, which is 1. 3 plus 3 is 6, which is 2. So what do we see? Well, of course, when we are using a 0, nothing happens. But if I look at the row here, 0, 1, 2, 3 in order, then everything shifts to the left, and the one that got pushed out comes back on the end. Then this shifts to the left, 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 one back, shift, left, 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 loopy back. And every number is in every row, and it's really just shifted around. Now multiplication is perhaps a little bit more challenging. 0 times anything is still going to be 0. I'm still performing the normal calculations, but my answer is restricted to one of these numbers. 0, 0, 0, because 0 times anything is 0. 1 times 1 is 1. 1 times 2 is 2. 1 times 3 is 3. Same for these. So everything is very similar. 2 times 2 is 4, which is 0. 2 times 3 is 6, which is 2. So I see that when I multiply by 2, I can only get 0s and 2s. Now there are deeper mathematical properties happening here that we are avoiding just so we don't get overwhelmed. But it's interesting to note that not all the numbers here are answers in a row. Here, every row had every number in the addition. In the multiplication, that is not the case. 0 times 2 is 6, which is 2. 0 times 3, sorry, 0. 3, did I say 0? 3 times 2 is 6, which is 2. Mod 4, 3 times 3 is 9, which is 1 mod 4. Because 2 loops of 4 give me 8, and then 1 is left. So some rows have all the numbers, some rows do not. And it's really a property of the modulus 4 that I don't want to get into too much right now. So we have these addition and multiplication tables. There are some patterns, some you may see, some you may not see. It's not that crucial that you see them. Next up is example 2. The 7-day cycle of common weekdays operates like a mod 7 system. Patterns in the mod 7 addition table are typical of all addition tables. Identical numerical results occur in diagonals. Modular multiplication tables, on the other hand, are full of interesting patterns that might be obvious sometimes and might not be. Let's have a look at the mod 7 table. Oh, we already have the exercise number. This is number 2. So now I'm working with numbers 0 to 6. 7 different numbers. So I have to keep that in mind. You can go through the motions. I don't want to waste your time here. And fill in your mod 7 addition table. And like before for the mod 4, which I think was there, you'll see it's just, where's my pen? There's my pen. This first row is the basic 0 to 6. Then it's shifted to the left. Shifted, and the 0 comes at the end. And then it happens again and again and again. Every number is in every row. Fairly simple, and you'll see this for any addition table in the same way. But the multiplication table, I just want to do a few of these. I'm not going to do the whole thing, and then I'll show you the answer. So when I tell you, you can pause and fill in the whole thing if you want to. So, of course, these guys are going to be all zeros, right? 0 times anything is 0. Whoopsie. 0 times anything is 0. That doesn't change. 1 times anything is just the same number. So, whoops, 2, 3, 4, 5, and 6. So some of these rows are as expected, and all the numbers appear in some rows, and obviously not in others. 2 times, let's do 2 times 3. 2 times 3 is 6. 6 is there. I'm just skipping some. I don't. Should we do the whole thing? Oh, it's a lot of work. You can fill in some of the ones I'm missing. 4 times 4 is 16. 16 is how many loops? Oopsie. How many loops around, and how many are left? 2 loops around will give me 14. 2 left for 16. 5 times 2 is 10. That'll be 3 mod 7. So the numbers don't go in increasing order because I'm looping around. Let's do one more. Let's do this one. 3 times 6 is 18. That'll be 4 mod 7. Let's do one more. 6 times 6. 6 times 6 is 36. 36 is what mod 7. So what's the remainder when I divide by 7? Well, 35 goes into 7 goes into 35, so 1 will be left. Pause the video now if you want to fill in the rest. Okay, let me show you all the other numbers. You see here in this case, contrary to the mod 4 multiplication table, all the numbers do feature in every row. And 4 and 7 are not the same. They have different properties. And there are a lot of deep mathematical properties happening here, and also applications that come from this modular arithmetic. It might be hard to believe, but in the security world, credit card security, encrypting information, all that is very strongly based on this modular arithmetic. So let's see what is left to do. Just our last little example, just to make sure that you can understand and perform calculations in whatever the modulus may be. So we have 13.2. First one is, let's just write that down. Let me zoom in a little bit. Exercise 13.2, number 1 is 9 plus 4 mod 6. 9 plus 4, well, I'm going to leave the mod 6 until I find my answer. 9 plus 4 is 13, which is equivalent to what mod 6? Well, 2 groups of 6 would be 12, so 1 is left over. So it's 1 mod 6. Next one, 6 plus 1 is what mod 8? 6 plus 1 is 7. And 7 is a perfectly valid number in my mod 8 circle, so I can stop right there. You can have your equal there, use an equivalency symbol, which is technically more correct for reasons we don't need to worry about too much. 6 minus 8, mod 5. We haven't done minus a lot, so it's good practice. What did I say? 6 minus 8. And I'm working mod 5. So I know 6 minus 8 is negative 2. But if I think about my mod 5 circle, let's put it over there. 0. Let's try and spread them out fairly well. Something like that. 1, 2, 3, and 4. Negative 2 is like starting from 0 and taking 2 steps back. So that'll be 3 mod 5. What you could also do is notice that if you're at a number, you can add any multiple of 5 to get you to one of these numbers, because any multiple of 5 in this case will just give you a full loop around. So negative 2 sits over here because a full loop of 5 around, whoops, let me do that again. A full loop of 5 around will put you in the same place. So you can, if you have a negative number as a calculation, according to your number line, you can add the modulus value to put you in among the correct valid digits or answers for your specific circle. Next up, number 4. 9 minus 5, mod 3. 9 minus 5 is 4. What is 4 mod 3? Well, 1 would be left when I divide, so it's 1 mod 3. One more. Number 5 is 5 times 10 mod 3. 5 times 10 is 50. What is it mod 3? So when I divide 50 by 3, what is left? Well, 3 goes into 50. It doesn't matter how many times, but I know I'm going to use 48, and 2 will be left. And one more. What's this line doing here? It's bothering me. Let's get rid of it. I see you, line. Last one. 8 times 5 mod 9. 8 times 5 is 40. What is that mod 9? What is that mod 9? Well, 9 has a multiple of 36. So I'm going to be left with a 4. There you go. There is your introduction to modular arithmetic.